Sort of what this talk is going to be like. It's really easy when you talk about things like formal methods to get off into the weeds and the theory side, or get off into the weeds on the details of the implementation side. This talk is going to try to sort of stay in the middle, and if you're looking for really deep theory discussion or really deep how to do formal methods for real, you might be maybe a little disappointed, but I hope that by the end of the talk you'll at least understand sort of the lay of the land. If you want to dive into the theory or dive into some implementation stuff on your own, hopefully you'll be able to. So that's the first disclaimer. The second one is I don't actually really know what I'm doing. Formal methods are an interest of mine, and when I was an undergraduate, I was really interested in them. I did a my capstone for my undergraduate, my big project at the end was a research project in formal methods. In the fall, I'm starting a PhD program at Purdue that is formal methods is going to be my area of study. So I'm definitely really interested in it, but right now I can't really make any claims to being an expert. I haven't really practiced formal methods day to day, as my job or anything like that. So just a heads up, if something I say is wrong, sorry in advance for that. Okay. So first of all, we're going to start sort of from the proof automation angle. I think there are a couple different ways to approach this topic. But we're going to talk about what proof automation is. We're going to eventually talk about what Coq is, which is a proof automation tool. We're going to talk a little bit about how Coq works. We'll get into an environment and actually do some proofs. And then we'll talk about how we can use it to generate code. But first, what is proof automation? Well, you've probably seen proofs before, mathematical proofs, maybe, I don't know, maybe not. This is you see them a lot in geometry or whatever, is where a lot of people encounter them in high school. This is a totally different proof. These are just images from Google Images of mathematical proofs. And when a human writes a proof, it's an argument that is trying to convince someone else who understands the mathematics that what they claim is true, right? So it's very, it's sort of an argument. You don't have to follow, there are rules of logic to follow, but if everyone sort of understands what the rules are to get from one step to another, you don't have to spell it out. So it's sort of informal. Well, it's formal, but it's not super every single rule is cataloged. So just real quick, how many people have written a proof that either mathematical proof or a logical P implies Q, symbolic logic? Okay. This will help you adjust. Okay, yeah. I just want to make sure I'm not talking too high or too low or whatever. Okay, so it seems like maybe half the room. So that's fine. That's cool. So writing proofs like this, where you don't, where sometimes you're just oh, to get from this step to this step, we can pretty much understand how that happens. It can be tricky. Sometimes there are things between the steps that you didn't think about, or some edge case or whatever. It's a lot like writing a computer program where you think it looks obviously right, but then if you actually look at it, you'll realize there's some small mistake or whatever. So
and then it becomes a clip.
Yes. Okay. So there's a class of tools called proof verifiers. I'm going to talk about this on a spectrum. It isn't every tool is either this or something in between. It's like a spectrum. Sort of on one side is something I'm going to call proof verifiers. A lot of people call proof verifiers, which is humans still write the proofs. They do all the work of generating the proof. The software, the tool, verifies that the proof that they wrote is correct, that they followed the correct logical steps. In other words, all those little in-between things got applied correctly. So here are a few tools that kind of, I think, fall on this end of the spectrum. There's something called MISAR, which is mathematicians use it to try to formalize mathematics. So some proof verifier use proof automation tools for different things. This one's pretty solidly mathematicians want to formalize mathematics. MetaMath is the same sort of thing, where it really is just rewriting terms. It takes terms and it rewrites them, and it just makes sure you did all the steps right. There's something called Hall-Light. Hall is a theorem prover, but there's this thing called Hall-Light, which probably still has some automated proving stuff towards this end of the spectrum, but I think mostly counts as something that does is very heavy on just verification. This is what a MISAR proof sort of looks like. This is what a MetaMath rendering of a proof, they have this proof explorer sort of looks like. And you can see it's a lot of especially on the MetaMath, you can see it's a lot of nitty gritty, here's something that's true, here's the reason why it's true, so on and so forth. You could follow this. Both of these are proofs of the irrationality of the square root of 2, by the way. The MISAR source looks a little bit more like something you'd write in math. You say there's a theorem, there's lets and let k be nat, and you could sort of mathematical. One of the big problems with proof verifiers is rendering proofs in a way that humans can actually understand, because when you actually do carry out all the logical steps, it gets like super long. So, that's what it sort of looks like on this end of the spectrum. Over here, you have the full like theorem prover side, where humans just specify what they want to prove, and then they push a button, and software goes and finds the proof, if it exists, and if the software can find it. I think a qualification for writing one of these is you have to have like a terrible logo, but a lot of these provers are like very bespoke. These are some of more of the general ones, but a lot of them are very bespoke for a certain problem. So like the four-color theorem.
The first one? Your shoulder's in the way.
Sorry, EQP.
EQP.
Yeah, so the reason I have this one up here is actually pretty early. I think it's like a predecessor of this prover 9. There's something called Otter in between, which actually a lot of people are familiar with. Automatic theorem provers might be familiar with Otter, but EQP actually did prove something useful. I think this is the one that proves something called like the Robbins conjecture. It's like there's this thing called Robbins algebra, and like the question was, is it equivalent to Boolean algebra? So if you don't understand what that is, it doesn't matter. But it actually did something useful in the realm of math. I'm pretty sure this is the one. Prover 9, like I said, there's sort of something called Otter in between. There's this thing called Prover 9, which I haven't actually used, but I think it's the predecessor or the successor to Otter. There's this thing called Theorema, which is a Mathematica plugin. So these are very sort of hit and miss, right? So they're the most hands-off. You can write just like, I wish this were true, and can you tell me if it is? But it's very sort of hit and miss if it's going to find it. Either that, or you have to write the proof to be very, very specific to this, like the one problem you're trying to solve. So a lot of proof automation tools fall somewhere in between these two extremes, and they'll be called proof assistants, or there's some other terms that get thrown around. But the idea is that it's sort of a back and forth between the human and the software. So the humans will say, like, here's what I want to prove. And then the software will say, okay, well, here's some stuff. If you can prove these sub-goals, like that'll sort of help you prove the major thing or whatever. There's like a back and forth. Isabelle is a really popular one. Coq, which is the one we're going to talk about today, I think is arguably the most popular. I think Isabelle is also quite popular. There's something called ACL2. I think Agda counts. There's sort of an overlap, we'll talk about this later, between proof assistants and dependently typed functional programming languages for reasons that we'll talk about in a second, well, later in the talk. But this is where a lot of the, I think this is where a lot of tools sort of reside, is sort of in this middle ground. Okay, so what is Coq? It is a dependently typed functional programming language, sort of. That's what, it kind of has a couple parts. Galena is this functionally, dependently typed functional programming language. It executes by sort of like the engine behind everything is this thing called the calculus of inductive constructions. It's the original, there's sort of this theory that was like the calculus of constructions, COC, also Coq. The guy who created this, it's a French research institute that this came from. His last name starts with COQ, so it's sort of like all these things that made this be called Coq. But anyway, what it does is this engine sort of, you'd almost, I think you could probably call it a type checker. I think that would be correct to say that's all it really is, but I'm not 100% sure about that, if that's a technically correct thing to say. But this is sort of like the engine, and then there's like a language that sort of sits on top of it. And we're going to see how it works in a second. We're going to actually like write some proofs in Coq. We'll just do a few to see how it works. But first I want to talk about the environment we're going to use, which is Proof General. It's an Emacs plugin. Whenever you read like a textbook on, or just any book on using Coq, usually it's like, there are a couple ways to do it. There's something called Coq IDE, which is something that the people who wrote Coq provide. It's like an IDE. And then there's also this thing called Proof General, which is a plugin for Emacs. And the book will say, we're going to use Proof General. So like, I'm not aware of anyone who actually uses Coq IDE. Presumably those people exist, but almost everyone that I read or listen to actually uses Proof General. And the way it looks is this. When we actually start writing stuff, I'll make the fonts bigger so you can actually see it. But basically, the way it's structured is over here on the left side is sort of like you as the human. This is your proof script, where you're going to sort of write stuff that you want to prove, or you're going to write tactics that help prove the things that you want to prove. Over here is sort of going to be like Coq's side. This is going to tell you, hey, here's some context and like stuff we're assuming that's true or whatever, like context relevant to the proof. And then below this line is going to be like a goal that we're trying to prove. And we're going to sort of like break down goals and try to prove them. Down here will be sort of responses. This is sort of like a status, like, yep, you proved it, or like, here's another sub-goal or whatever. So sort of like a status line. Okay. So with that orientation, hopefully, let's look at writing some proofs. Actually, I'm just going to full screen this. Okay, the live coding part, this always goes well. All right. So what I have here is I have just a .v file loaded. I'm going to make the font bigger. Okay. We'll see how this goes. Okay. So the first thing that we're going to do is just look at what it's like to write a proof. It's going to be really hard to fully communicate what Coq can do, like how to use Coq could be like this like multi-day like workshop or like probably a semester-long course or whatever. So hopefully this will just give you an idea of what it looks like to use Coq. Even if you can't follow along with all the way like things are happening, that's totally fine. The idea is just to sort of get a feel for how it works. So the first thing I'm going to do is going to define a theorem. Is that big enough? Oh, great. What I'm going to call it is and associativity. And what it's going to be is for all P, Q, and R. So I'll type this out and then unpack it in a second. So hopefully, if you know what associativity is, you might see where this is going. Okay, so what this says, and let me see if this gets accepted. Weird. It did get accepted, but I got this extra window. We'll just pretend that doesn't exist. Okay. All right, this might be fun because of font sizes, but we'll see. Can everyone see this okay if it's this big? Is this cool? Okay. So what this is saying is I have a theorem I want to prove. I gave it a name called and associativity. And what the theorem says is that for all P, Q, and R, so note that there's a universal quantifier out here. You can do that in Coq. You do existentials too. Which are propositions. So this is P, Q, and R of type proposition, which is just Coq's general, like, this is, it's like a proposition of like what it would be in logic, something that's true or false or whatever, right? Or not whatever, just true or false. So this, these little slashes that go like this are supposed to look like an and sign from like formal logic. So P and parentheses Q and R implies that P and Q parentheses and R, right? So you can just move the parentheses back and forth. So this is like a really basic theorem. This is like, you can, like two things ANDed together, you can do it in any order, right? So this is like, if you think of Boolean AND, it's like if you have three variables that you're ANDing them together, it doesn't matter which order you do the AND in, right? This is all this is saying. Okay, so I want to prove that this is true. So I'm going to say proof. And over here, Coq is telling me above these equal signs here, there's nothing here. So I haven't assumed anything, I don't really know anything, the context up here is just empty. Down here is the thing I want to prove, which right now is the complete goal. It's for all P, Q, and R, it's the whole thing, right? So the first thing I want to do, if you've ever had a symbolic logic class, you might think like, oh, the first thing you do when you want to prove for all something is you just have like an arbitrary element of whatever the thing is. So like if you want to say for all numbers something, you say let n be an arbitrary number, and then you prove stuff about n, right? So the analogous thing to do here is a tactic, and the things you do in Coq are called tactics. It's called intros, P, Q, and R. So what happened when I said intros, P, Q, and R? Oh, and by the way proof general works is if you see this blue background, which is sort of maybe hard to see on the TV, those are things that Coq has accepted as true. The things I'm typing below are things that I want Coq to evaluate but hasn't evaluated yet. And there's a function just in proof general to sort of like go back and forth and admit things or whatever. So when I admitted this intros P, Q, and R, what happened over here was the for all P, Q, and R like moved up to here. So now I know that these three things are propositions. That's something that's in the context I assume is true. And my goal changed to this, which is this without the universal quantifiers. The parentheses aren't here anymore, but that's just because the order of operations sort of implies them. They're still there, really. Okay, Also, the way I would write this proof, if you're like a cock pro, you might be like, there's such a cleaner way to do it, which you're right, there is, but I want to make it sort of maximally clear for this. So sorry if it's making you cringe to see this happen in slow motion. But the next thing I'm going to do, so my goal now is an implication. So something implies something else. So this is like, if A, then B. The way you prove that is you say, well, assume A is true, and then show that B is true. So intros again. And what happened, what was on the left side of the arrow is now up here as something that I'm assuming is true. And my goal changed to this. OK, after this, what I'm going to eventually want to do is split up. The way you prove like P and Q is to prove P and then prove Q, and then P and Q is true. For that, I'm going to want this to be, instead of P and Q and R, I'm going to want separate things that say P and Q and R. The tactic for that is called destruct. So I'm going to destruct H, destruct H0. And now I have P and Q and R over here. And again, if you can't quite follow along, that's totally fine. The idea is just to show there's sort of like this back and forth happening. So now the name for splitting this up is called split. So now I have two subgoals. So what I did is I said I had P and Q I wanted to prove and R I wanted to prove. I said split them up. So now I have one subgoal here. I have another subgoal here. The way I focus a subgoal is to use this like bullet. So now it's just P and Q. I want to split this up again so that I have just P. And you can see what's happening over here is just as I go through the proof, what's up here is changing, what's down here is changing, and that's helping me decide what I'm going to write next over here. So I want to show, so I'm now in the place where I want to show P. I have a hypothesis up here that says P is true. So I'm just going to say apply it. And that subgoal is finished. Here's the next subgoal. I have that one too. This proof is super easy. R, I have that one too. OK. I don't know why it's a small all of a sudden, but it says no more subgoals. Probably because this is now my status window and no longer my context window, because something weird happened. So that means it's done. I can say QED. And the status I get back is, and a soak is defined. In other words, Coq accepts that, yes, your proof is valid. OK. So I know that was probably a little like, maybe like a little in the weeds for how this goes through. I think really the important thing is just to see how there's sort of an interplay between what I'm doing over here, what Coq is telling me over here. OK. You can also like prove stuff about natural numbers. I think I'm going to skip that for now because I don't think we need to see that. But I do want to talk about what happens when you when I actually talk about something related to programming. So this is like a logical fact. We can prove like mathematical things too. What I was going to prove, I won't actually write out the proof for this, but you can do stuff like, this is another easy one. So this is saying for every n, that's a natural number, n times 0 equals 0. And it's actually interesting. Going the other direction, I'm going to write the proof, because this is so if this were just 0 times n equals 0, the proof for this is actually really easy. You interest n. Your sub-goal becomes 0 times n equals 0. There's a tactic in Coq called simple, which means go into your little calculus of inductive constructions and like see what happens if you can rewrite this something simpler. In this case, it's like, yes, I totally can. 0 equals 0. And you're like, awesome, that's what I wanted. There's this tactic called reflexivity, which just means if you have two things inside of equals that are the same, then it's true. So that's like super easy proof. If you try to go the other direction, n times 0 equals 0, which like should be like the exact same thing, right? What happens if you try to simple here? Nothing. So it admits simple, but it's like, I can't figure this out, right? So this is why it's sort of like a proof assistant, is you're like, hey, assistant, assist me with this thing. And it's like, oh, okay, I couldn't do it. And you're like, okay, well, now I have to do it for you, right? And in this case, the way you have to do it is by induction on n, actually. If you're familiar with that tactic, this will probably look familiar. If you're not, then don't worry about it. But I'll get a couple things. Induction is a lot like recursion in programming. So there's like a base case, and then there's like a non-base case. So the base case is easy. If you simple this one, definitely is true. So now we're at this case where what we want to show, or we have this inductive hypothesis, and if you don't understand induction, don't worry, it's just true. Cock told us, and Cock is always right, that n prime times 0 equals 0. You can just assume that's true. What we want to show is that s of n prime times 0 equals 0. S of n prime is just the successor operation. It means n plus 1. So we can ask Cock to simplify this. And it knows that actually the successor of n times 0 equals 0 is the same as n times 0 equals 0. How does it know that? Well, it did its thing, and it's our assistant. It did something for us, right? And we're like, oh, that makes it really easy because we can apply IHM. And by the way, it's not actually that magical. If you understand the full calculus backend, it makes perfect sense, but we're not going to dive too deep into it. So anyway.
If you knew A times B is equal to B times A,
you could have rewritten.
Prove it, just rewrite it.
Yeah, so and that's the, just like in a mathematical proof, there are a lot of different tactics you can take. So one of the ways, if we knew that multiplication is commutative, we could have rewritten this as, but that proof that multiplication is commutative will look really similar to this. So it's sort of the same thing, but we could have taken that shortcut if we'd known about the commutativity there probably is, it's probably called something like multcom or something, and if you know that, you can totally apply that and it works.
If you had proven that previously, would Cock have figured that out? And then when you ask for assistance, it would say, oh, I can just flip it.
You have to tell it. So that's it won't just look at its entire knowledge base and say oh, I know what I can do. You have to tell it, no, this is the thing to do. And if we want to prove something based on this, we can totally use this mult n0 fact later on in our proofs if we need it. Yeah.
Is there a reason why it doesn't look at its knowledge base? Is this
it's
a
just too much
contractibility thing?
Yeah.
Okay.
It's just, and there are ways that.
Surely there's a way you can prune that search space somehow. Like this is.
So yeah, there are definitely ways that you can do this where you try to generate the proof, and it's moves into that spectrum of theorem proving. But there are totally ways that exist within Cock to do exactly what you're saying, and we're going to sort of not talk about those right now. But yeah, it's totally a thing that you can do. Okay, but what I really want to talk about is this seems all well and good and mathematical, but what about programming, which is what we're here to talk about. So we want to know how we can say stuff about computer programs using theorem provers. That's the reason we're here. What I'm going to do is talk about lists to start with, because lists are a nice sort of in that intersection of really useful in programming, sort of easy to model with this inductive way that Cock gives us to model stuff. And hopefully you can sort of use your imagination to figure out how things that aren't lists would be applicable, or what we could do. And we'll talk about some of that stuff too. But for now, we're going to talk about lists. So how do we prove things about lists? We need a way to talk about them in sort of a mathematical way. Cock gives us a way to define inductive data structures. And the keyword is inductive. And it's a lot like algebraic data types in a functional programming language. So if you're familiar with Haskell or ML or one of those dialects, it'll probably look pretty similar. What I'm gonna call this nat list as a list of naturals. There's a built-in list that we're gonna use after I define this, just to show you what it looks like, because there's a bunch of niceties with notation and stuff. But the way it's gonna look is you're gonna have some sort of nil. I'm gonna prefix it with n just to say it's for nat list. And nil is just a nat list. We're also gonna have something called cons, and that's gonna take some natural and a nat list and produce a new nat list. So this might be one of those things that if you're familiar with functional programming, you're yeah, totally. If you're not, it might be sort of confusing. You can see this this arrow as an implication, or you can see it as a function. Probably functional is easier to do here. So you give it a nat, you get back a function that takes a list and gives you a new nat list, which is going to be these two things cons together. So I hope that makes sense. Now that we've defined that, we're going to sort of ignore it and use the list that Cock gives us, just because it's a little bit nicer. And there's a little bit of housekeeping that goes along with it. So, sorry. Okay. So what's something that we might want to do with a list in a computer program? The example I chose, because I think it's sort of illustrative of the kind of stuff you can do, is reverse a list. So let's say we want to have a function that reverses a list. We want to prove stuff about it, that the function works and is correct. The first thing we need to do is tell Coq what does it mean to reverse a list. And then we can start talking about, we can prove stuff about it. So fixed point is the way Coq gives us to do this. And this is fixed point in a, the reason it's called this, I guess, is that we want our recursion to always terminate. And Coq is very strict about the way that it lets you do induction. So terms that you use in induction always have to depend on things that are like less than that term. You'll see what I mean in a second when I type it out. Okay, so what this is telling Coq is that I'm going to define something that's recursive, inductive. I'm going to call it rev for reverse. It's going to take in a list of naturals, and it's going to return a list of naturals. We're going to call what it takes in L. You can see this in a function definition, right? Like rev takes in a list, returns a list. Okay? And the way we're going to do it is by matching on the list. If you're a functional programmer, this would be super old hat. What do you do to reverse an empty list? Nothing. The empty list is just its self-reverse. What about like a natural cons to like a whole other list, like a tail? So that's actually pretty easy too. It's just the tail reversed, appended to the head. And I think I'm going to go ahead and type it this way to save a syntax edit. Okay. So I believe that this is Coq accepting it, I hope. Let's double check. And you can see it says rev is defined, rev is recursively defined, decreasing on the first argument. This is what I was clumsily trying to say at the beginning, is that when we have some recursion here, you have to be careful that the right-hand side of this is some decreasing thing on the left-hand side. Otherwise, it might not terminate. And Coq makes the guarantee that all of its terms terminate. So that's important to know about Coq. Okay. So here's the interesting part. This is like sort of like a formalization of a function that you might write in either a functional language or not a functional language, whatever. We want to prove stuff about it. We want to know that it's correct. So what might you do if you were writing this in an imperative language? You might write some unit test or something, right? You might, let's say one property we want to hold is that when you reverse to the append two lists together and then reverse it, that should be the same as if you reverse the second list and then append it to the reverse of the first list, right? This is just a property we want to hold. Okay. How might you test this in imperative language? Well, you might construct some lists. You might have like some things you might think might be edge cases, like empty lists. You might give it just some like random lists that you think of off the top of your head and see that it works, right? That means it works for whatever cases you picked, but obviously there are like an infinite number of lists or effectively infinite number of lists depending on how much like memory is in your computer. Can you prove it for every single list that could possibly be reversed is the question. So we're going to do that by introducing a theorem. We're going to call it reverse append distributive. You can call it whatever you want, but that's what we're calling it. So all we need to do is quantify these lists. And this is just a type. So what I stuck at the top of what we wished was true here is just saying for all L1 and L2, which are lists of naturals. And we could actually prove this for lists of any type, but we're just going to stick to naturals for now. All right, how do we prove it? Well, we've seen how to prove stuff in Coq. It's the same sort of thing. I might actually cheat and copy and paste the proof so that I don't have to type it out. Will it take exactly as long to do it? So we'll find out. So cheating. Oh, hey, I'm going to cheat and pull out some of this notation too. Pay no attention to that. That'll make things easier for later. Okay, and I'm just going to pull out both these proofs because I think we get the idea of what writing proofs looks like. And it doesn't matter that you understand the proofs so much as you understand that proving works and sort of how it looks. And I'll just go ahead and fast forward to the very end here. Okay, so everything got accepted. You can sort of see the general way that we went about proving this application or append is distributed. We introduced stuff, then we did induction on one of the lists. We used this like fact about lists appending nils. We did some rewriting, whatever. We did some stuff. If it seems like magic to you, that's fine. Just trust that if you spend a bunch of time messing around with Coq, you would figure out how to do this too. It's just practice on applying like these tactics and stuff. Okay, but I actually snuck another proof in here while I was doing my little copy paste, which is that it's also involutive, which is a fancy word. That means if you apply it twice, you get the list back. So that's a good property to know too. If you were writing this in imperative language, you might say like, oh, it should be the case that if you reverse the reverse of the list, you get the original list back. You might throw some lists at it to make sure it generally holds for the things that you try. But this is a proof that it holds for literally every possible list you could possibly throw at it, right? So it just is correct. Okay, and something important to note too is that we sort of defined reverse as being something that lets us talk about what a reverse list is, what it means to reverse a list. But it's something that lets you actually reverse a list too. It is a program as well. You can say compute the reverse of like some list, and it'll tell you over here in the side that yeah, it did it. So like, not only is this sort of like a definition of like in a mathematical way of what it is to have a reverse list, it is actually a program for reversing lists as well. So that's sort of a key idea. What that key idea is called has a fancy term. If you don't like mathematical sounding words, just plug your ears. But if you do want to know what the term is, it's called the Curry-Howard correspondence or the Curry-Howard isomorphism. These are two people who discovered it. This is Haskell Curry. This is, I want to say William Howard, but don't quote me on it. His middle name is definitely Alvin, though. I don't know why I remember that. But they sort of came up with it. And what it says is that for a certain, basically what it says in a sort of hand-wavy way is that proofs and programs are basically the same. There's an isomorphism. There's a one-to-one correspondence between stuff in a proof and stuff in a program. What's like implication in a proof is like a function in a program. Okay? And you can sort of go back and forth between these two worlds. Some programming languages make the translation to a language like Coq easier than others. But basically, with some constraints, some caveats, this holds. Actually, one of the caveats is the logic is based off of like this constructed intuitionistic logic. It's constructive logic. So what that means, if you're familiar with the classical versus like intuitionistic logic, is that the law of excluded middle doesn't exist. That's P or not P. So you might think it's true that any proposition, surely it's either P or not P for any arbitrary proposition. You cannot prove that in Coq unless you cheat and just tell it to accept that fact. And that's a consequence of the way Coq works at its very core in order to make this correspondence sort of work out.
What they do in intuitive logic is they redefine implication. And implication means that you have a procedure that takes, if A implies B, you have a procedure that takes an A and gives you a B.
Sure, yeah.
And if you don't have that, then not knowing that you can't do it or you can do it or you can't do it means that you can't say A or not A.
Right, right. So there's sort of like techniques to sort of like still have expressive power. But the reason P or not P isn't allowed in intuitionist or construction, let's call it constructive logic, is because everything must be constructed. So A or B means you have a proof of A or you have a proof of B. If you're allowed to say P or not P and you don't have a proof of either P or not P, it's broken. Like that's non-constructive. There's some other things that are sort of equivalent. There's like not P, like double negation implies P. That's the same deal. No bueno in constructive logics. There's something called Peirce's law, which is like P implies Q implies P implies P. It's sort of like with like brackets. So I think I said that right, but like that's also sort of equivalent to all that. So there are techniques to sort of like still have expressive power in that world, but everything has to be constructive. So that's sort of the caveat. So the question is like, can we actually use this and beyond this like very sort of like esoteric proof theorem prover kind of way, right? So one thing you might try to do is say, well, I have a program. What if I can translate it into the language of mathematical proofs and then start writing proofs for it? Instead of writing my unit tests that check for a handful of things that something is true, can I translate my program into something that I can write proof for, that the thing I care about is always true? So like when you reverse the reversal of a list, you get a list back. If I have a reverse function over here, can I translate the reverse function here and then prove stuff about it? So there is something called Krakatoa that I haven't used, but I was researching ways that you could do this for like Java or C. This seemed to be the most promising way I've found, but I've never actually used it. But you sort of have this annotated Java program or C program. It does a bunch of junk, and at the end, you get these encodings of your program into something like Coq or Isabelle or whatever, and you can write proofs for it. This translation is easier for like functional languages. The closer something looks to sort of like what Coq looks like, the easier it's going to be to sort of translate them. So something like Haskell or whatever is easier for this. But anyway, so this is totally something you can do and that people do. The general idea is like you have this certification that your code meets some properties that you care about. So you have your code, you have proof, like you have your translation of that code into something that you can prove things on, and you have a bunch of proofs that you wrote. And in a way, like it certifies that your program does what it's supposed to do. And people spend the time to do this, which is very like time-consuming, as you might imagine, for things that matter a lot. So maybe if you're just writing like a web server, you don't care if it like whatever mathematically like matches your thing. But like if you're controlling like the space shuttle or like the Falcon Heavy, I guess a more contemporary reference, like maybe you do want it to be like provably yes, this is how it works, right? So we kind of talked about like going this direction and then writing proofs, but you're going to write the proofs anyway. What if you can go like this direction? You start out with something that you wrote, you have a bunch of proofs for it, and you want to generate a program that just sort of like, you don't actually do anything, just a program gets written for you based off of the stuff that you wrote on the proof side, and the stuff you proved about it is true, right? So this is where extraction comes in to the picture. And I guess sort of the punchline of what we're talking about is that, like, yes, you can do that, and it's actually built into Coq. And we're going to take a look at what it would take. So we have this very simple world, and reversing a list, maybe not super interesting, but hopefully in your imagination you can extrapolate this to other types of programs. What we want is this reverse function, right? In some language that isn't Coq. Okay. So in the interest of time, I think I'm going to cheat and do a little copy pasting again. We're just going to do the very simple version here, which is 2 lines. We're going to, well, there's going to be, we're going to require this package, coq.extraction.extraction. We're going to set the extraction language to Haskell. There are 3 languages, I believe. OCaml, which is what Coq is written in and works the best. Haskell, which is a language that I'm familiar with, unlike OCaml, which is what we're going to use, which works pretty okay. And it also can target scheme, which I hear is kind of hit or miss. I haven't really used the scheme extraction, so I'm not 100% sure. So we're going to tell Coq to do those things. And then we have one more line, which I'm just going to copy and paste as well, which we tell it what file we want to extract to. So I'm going to create a file called rev.hs, which is a Haskell file. And I'm going to extract rev, along with anything else that rev needs in order to work. So I really wish my status area wasn't all screwed up. That'd make this easier. But what it's telling me over here, there we go, is that it created a file called rev.hs, which is a Haskell file. So I'm going to, actually, before we interpret this, what I'm going to do is open this up. Having all these Emacs frames is certainly going to come back to haunt me a little bit, but that's in the future, so who cares? All right, rev.hs. So here's what it generated. Pretty small. What we did was pretty small. Here's the rev function itself, which looks similar to what our Coq function looked like, our Coq definition looked like. It sort of has this recursive, if it's nil, nil, if it's cons, then reverse the tail, and then cons on the head at the end, or append the head on at the end. It needed some other stuff. It needed append, which is something that Coq gave us, the Coq library has. So it does this. It needed to know what naturals were, and it needed to know what lists were. So this is going to be interesting because this isn't Haskell's nat. This is just a data type that Coq wrote in Haskell that represents natural numbers, and the same for lists, right? So if we try to open this up in an interpreter, oh hey, how do you make fonts bigger in Shell? That's going to be interesting. What are some preferences? I bet it's not advanced. All right, well, this is something I could have definitely figured out ahead of time. Oh, really?
Yeah.
Oh, yay. Thanks. Okay. Cool. So I'm going to open GHCI, which is the interpreter for Haskell. I'm going to load our thing. Okay, so it works, right? We have something called rev, but here's the problem. It's going to expect a list. We can't just give it a Haskell list, which would look like this, because we're saying we want a list of integers. It's saying it expects the type of this thing that Coq created for us. So we could, if we wanted, by hand, start consing things together. Oh, it's not, it's O, capital O, because it can't be 0. So let's just say we want to do something really simple. Oh, and we still can't even because there's no show. So we would have to be deriving show for these things. Oh, and also prelude is imported qualified, so it has to be prelude.show. So this is pretty annoying and bad, right? So I could reload rev. I could try it again. And hey, if you reverse a list with just 0, you get 0 back. Okay, yeah, that's true. We could build up a bigger list, but I don't feel like doing all the manual consing and whatever. Okay, so how do we make this better? One of the things we can do, and I'll go ahead and keep on cheating by copying and pasting, is that we can tell it what a list is. All right, so before we do the extraction, we can say hey, when you get to a list, don't do your list, that's dumb. Here's what a list type and what the constructors are in Haskell that map to the types in our inductive declaration of what a list is, okay? So if we give it just that one little hint, it'll recreate this file. And I will be able to find it again, I hope. Okay, and now it's a little bit better. We still have this nat stuff hanging around, but now the lists are Haskell lists. So yay. that's definitely an improvement. So if we wanted to do a reverse, I don't know if we want to go through the exercise, but if we wanted to like reload this, now we can start giving it, this is like too hard to see because it's like low. Better. Okay, so now we could say like rev, but then we'd still have to give it like these, whatever, these naturals. We could have like a 1 in there if we wanted. And it doesn't derive show, so it still breaks, but whatever, it would work. I don't think we need to go through that exercise. Okay, so the last thing that we want to do to make this actually nice is sort of not the way you probably actually want to do it, and it's sort of broken and long, so I'm just going to like paste in this stuff. You can sort of read it and guess about what it might be doing. It's sort of ugly, right? But it does work. We've regenerated rev.hs. Let's see what it looks like. All right, this seems reasonable. There's no more nat. There's no more hand-rolled list. It just it uses Haskell lists. It uses integers, prelude.integers. This is more like it. So over here, we can say reload rev.hs. And now we can reverse a list. 1, 2, 3, whatever. This is in Haskell. Okay, so we kind of got there. It was sort of a pain. We had to do some help Coq translate some stuff over. But once you set up that translation layer, then things actually work out pretty nicely. And the important thing to note is that our Haskell code that we have now, we could write like, do some like Haskell stuff. We could write like some like quick checked properties to prove that those things about lists, but it'll just always work, assuming there's no bugs in the translation and the extraction, right? Or in the Haskell runtime or whatever. It just like we have this code in Haskell, but we also have a proof that it has certain properties for literally any list you could throw at it. That caveat, by the way, about depending on no errors in the compiler or the interpreter or whatever, depending on what you're doing, might be a huge deal. It might be like, who cares? If you're writing a web server and your service is correct as long as there aren't any bugs in the compiler, that's probably like best case scenario or whatever. So, okay.
Yeah.
Yes.
So when you say it's correct,
Mm-hmm.
what does that actually mean? Like if I give it a large enough list, have I proven that it will never blow the stack?
So,
or if I give it a large enough list, I can prove that the program will finish in my lifetime.
right.
Or
So,
my grandchildren's lifetime.
right. So what correct means in our case is that these things that we proved are true. So these proofs don't say anything about like runtime. They don't say anything about like
Memory
what happens.
usage.
Yeah, memory usage. Like right. They don't say anything about that. So so if we can reduce the problem to specifying the right stuff, we still have to specify the right stuff, right?
Mm-hmm.
And that's definitely like a limitation of formal methods in general, is that if you want to prove that something meets a spec, it moves the problem into writing the correct spec.
Excuse me,
Yes.
is it possible to write a spec that would simulate the idea of like a stack not overflowing and stuff like that in this system?
So that's a good question. You can definitely write proofs that involve like the length of lists. I don't know.
I mean, I was just curious if you could like, is this, if you could even describe it in terms of modeling?
Yeah, so like in Coq you can model. So like you could imagine setting up a model using like our definitions or whatever that models a full like some machine that has like a stack and actually Coq has been used to do to verify x86 architecture and LLVM architecture. And my guess is it does it in this way, by setting up a model of those architectures and then writing proofs about it.
All right.
Yeah, so anything you can model and then write proofs for, you can model and write proofs for,
Okay.
right? I don't know if you can use, if you set up like this complicated model, if extraction would be a useful technique to you at that point.
Yeah, no,
because
I would right now.
But you could definitely formalize things in models and Coq and then prove them. Okay, so that's sort of the where things are in terms of like, it's pretty much in Coq. It's a little bit like nascent maybe. It's not super nice to use. Where do things look like? What do things look like on the horizon, or like what's some active areas of research? There's this thing called Fiat, which is a Coq library. And you can ignore all the symbols except for this one at the top, which helps you synthesize correct by construction programs. So correct by construction being this term that means you've built the software by proving stuff about it, and it's correct by nature of the way that you built it, right? So the way Fiat sort of looks, and all Fiat is right now is like a library and a paper, so it's not like a mature product or anything. But the idea is, and these examples are from the paper, which you can find here, or just Google. If you Google it, make sure to Google like Fiat formal methods or something, otherwise you'll get like the car company or whatever. But the idea is that like you have this, this is a spec about, I think in the paper the example is it's a cache. And if you insert a key and a value into a cache, then what should happen at the end is that the new cache should be a subset of the old cache unioned with the key and the value. So it seems like a very high level thing for a cache. Like there's so many other decisions you need to make about a cache. But the idea is that with Fiat, is that you can start with something like this and then start refining it. And refinement is an industry term that means like going from the specification to like an actual like executable program, right? So this is an example figure from that paper where maybe you start with like this general thing, and there are a couple of different routes you can go to start refining it. Let's say you pick this one, you go down the refinement chain until you get to something that's actually like an executable piece of code or very close. So in the same way that Coq sort of steps you through writing a proof, Fiat would sort of like step you through writing a program by doing the refinement, and you make decisions along the way. So that's something that's out there. There's something built on top of Fiat that's a paper. All it is a paper. There's bytecode. I don't know. Using Coq to write fast and correct Haskell, and the idea of this is that you combine Fiat's like refinement techniques with this technique that the paper describes using something called free monads. Whatever, it doesn't matter. The idea is that you can, it helps you start generating, it does more of the work for you for generating these programs. And the example they use in the paper is byte string, which is famously in Haskell, like if you try to write byte string, as in just a string of bytes in Haskell, it ends up being incredibly inefficient and terrible. And you have to do this like non-intuitive thing in order to make an efficient byte string. And this paper sort of describes a way to automatically derive that same sort of implementation. So there's actually a podcast called the Haskell Cast. This guy, John Weigley, talked about this exact paper in one sort of a recent Dish episode, if you want to go look at that. Other things that you can do with these techniques, you could try to extract properties of code that exists already. So you could try to go the other way. And this is sort of like frontiers of research. I'm not aware of code that does a lot of, well, there's probably like research code out there that does this, but I'm not aware of like productionized things that do this. But you could say like, here's a piece of code, do some formal analysis, and tell me what the specifications are based on just what the code does. There's this idea of like program repair. What happens if it's like spell check for your programming logic? Like what happens if your logic doesn't match your specifications? Can like you automatically fix your programs? Stuff with like compiler verification. There's like this whole chain. Well, I'll talk about this in a little bit. But there are people who want to sort of have a full chain of like high-level language, compiler, sort of like all the way down to the machine code level of like verifying everything along the way. And yeah, things that might happen in the future with these types of formal analysis techniques. You could, I know someone that I've been talking to at Purdue wants to sort of think of a data type definition as this sort of like abstraction that's sort of like a specification. Here's how the data type, what it's supposed to do, and what you can do is sort of like automatically generate something that meets that specification in a way that's bespoke to the way you're using the data type. So like, for example, if you're making like a cache, and the cache does some check, but the analysis of the way you're using a cache says like, oh wait, we actually don't need that check because it's impossible. It'll throw the check out and you'll get a more performant thing. But you as a programmer don't really care. You just say, here's a data type, an abstract data type, generate an implementation for me that works for my thing, right? So that kind of stuff is sort of an area of research. I think there's some other things. I think I wrote in the speaker notes. Oh yeah, more sophisticated refinement. That's what I was going to say. So like you could see doing the refinement process right now, sort of like like manual and like you have to make all these decisions. Maybe there's like a more push button way where you can just say like, hey, here's a program I want, and like, or here's a property I want, generate a program that meets it or whatever. So these are all active areas of research. If you're interested in this kind of stuff that you can read, there are these books called, like these software foundation books by this guy named Benjamin Pierce and a bunch of other people. This first one, Logical Foundations, I actually think is a really good introduction to just Coq in general. If you want to know more about Coq, a lot of what I know about it comes from this book. It's free online. You can go to this website, read it. The third book in this series is actually about, it's called Verified Functional Algorithms, and is about what it says. So if you're interested in this topic, that's something to check out too. There's this guy named Adam Chapala at MIT who has this, his group is doing, his group is where Fiat comes from, but they're doing this sort of full chain all the way down to, there's this thing called like Bedrock, which is like an assembly language that has like specs and proofs and whatever. And the idea is to have like this whole chain from high level to low level where everything's verified. Other things you could read, I kind of glossed over, like the Fiat paper, that Coq paper is interesting. There's these people doing like this verified software tool chain, which is very similar to like having this verified chain like from high level to low level. The Purdue Programming Language Department has like this website that I think has a lot of interesting research on it. Those are places you can check out too. Okay, so I know we're a little over time. Sorry about that. I think we had a late start, but I can try to answer some questions if anyone has any. Remember, like I'm not a super expert in this kind of stuff, so I'll definitely do my best to answer questions. But if I don't know the answer, sorry. Are there questions?
So are you doing this just because you're interested in it, or are you actually using this in your day job?
So I'm actually not using it in my day job, but I am interested in it. I'm actually starting a PhD program at Purdue in the fall, and so some of the people I've been talking to are working on this stuff, and I think it's really interesting, and it will soon be my job, I guess you could say, as a student.
As a student,
yeah.
Not what you do now.
Right, yeah. So in my career, I've seen formal methods be used in real life, like twice maybe. And so at Square, some of our payments processing code was formally verified, and some of our reader circuitry code was formally verified. And integrated circuits is a really hotbed of like formal methods. So verifying things about circuits. And obviously, like it comes down to like a cost trade-off. If you're going to manufacture a physical chip, it's worth taking the time to start proving stuff about it. It takes time to do it, yeah. And I think the question, the research question is like, how can we make the cost of doing this formal analysis lower to sort of like, to make it start making sense for things that aren't that like, well, we're sending something into space, or like we're going to produce like $1 billion worth of chips and it has to be right or whatever. So,
or life support things.
Yeah. So right now, the cost is high enough, it only happens in these like really critical things. Is there a way to lower the cost? I think is one of the big questions right now. So. Are there other questions?
Is there, I mean, to your knowledge, is there any overlap between Coq and artificial intelligence? I mean, clearly not neural nets, but like other forms?
So I think there are a couple of relationships. One is there are people doing, so one thing that you can do right now is try to search for proofs or search for programs, which are, because of the Haskell-Curry correspondence, or the Haskell-Howard, yes, the Curry-Howard correspondence, it's sort of the same thing, searching for a proof, searching for a program. So there are ways that there are like interesting machine learning problems in that domain. There are also sort of the other direction. Let's say that we are training a neural net to do something like drive a car. Okay. Is there a way that we can have formal methods that ensure that the way a neural net gets trained is not going to like crash the car or whatever? Is there stuff we can prove about neural networks?
Okay, so the training could be a part of the...
Yeah, or even post-training, you have a network and you want to prove stuff about it. Are there ways you can do formal analysis about on those types of programs, which gets hard because of the nature of neural networks. But right. There is actually research at Purdue, I believe, right now about this exact topic. So.
Wow, thank you.
Yeah.
So you can prove that 2 cars that are self-driving using this algorithm will never crash.
Well, it's you want to prove properties about the neural network. One of the interesting problems might be what does it do under certain constraints, right? Yeah.
Unless it's Bruce. No,
we'll figure out a way. We will find a way.
Kidding. We all like you, Bruce.
Can I talk to that slide about logical foundations? I'm gonna get the URL, or these slides may be available someplace.
I can, yeah, I can put these slides up. I can share them with someone after.
What?
They do record as well.
If you Google like logical foundations or this guy Benjamin Pierce, who's at UPenn, you will find these. This is on his like website.
Okay, thank you.
Yeah. Are there any other questions? All right, thanks everyone. Appreciate your.